In this video, we are going to review the concepts of vector spaces that we're going to need as we proceed doing field theory and hopefully, if we have time, module theory. Again, just to make the point clear, this is not really a video meant to thoroughly introduce you to the concepts of vector spaces. It's more of a refresher course on things that you should remember if you have previously studied vector spaces in the past. Let's start with the definition. Let's suppose that V is a set, and we want the set to form an abelian group. The operation that we're going to use here is addition. We're going to denote this by plus, although there's going to be a little ambiguity here. Let's suppose that F is a field, and that F acts via scalar multiplication on the set V. So I have to be a little bit careful when I use the word acts here, because in abstract algebra, the word act has a very specific meaning. But here's what I mean. F acts via scalar multiplication on the set V if every time I take an element A in the field and a vector V in the set, there exists a unique vector, which we're going to denote by AV, in the set V. Now, we say that V is a vector space over F, so there are two things that are important here, both the set and the field, vector space over F, if the following properties hold. So whenever we see the letters U and V towards the end of the alphabet, they belong to the set V, and the letters A and B towards the beginning of the alphabet belong to the field F. The first thing that we require is we require multiplication by the scalar to distribute over the addition of the vector space. So that is, if I first take two vectors V and U and add them together, and then multiply by the scalar A, that should be the same thing as if I multiplied each of them individually, V and U, by the scalar A, and then added them together. So the scalar multiplication distributes over the addition of the vector space. The second thing is we want the scalar multiplication to distribute in the other direction. That is, F is a field, so it has two operations, addition and multiplication. If we take A and B in the field and add them together first, and then choose to act on the vector V, this should be the same thing as if we acted first by A on V, then by B on V, and then add the two together. So distribution in both senses over the addition of the vector space and over the addition of the field. The third property we require is we require the action to be associative. So if I first act on the vector V by B, and then later act by the vector A, this should be the same thing as if I first perform the multiplication within the field A times B, and then act on the vector V. And last but not least, we want the multiplicative identity of the field, which we're denoting by 1. We want that to fix each of the vectors inside the set. So if we take any vector and act on it by the multiplicative identity, we want this to not change the vector that we're looking at. Next, let's move on to some examples. Let's start with the really basic and more familiar examples, which also make the concept of vector space quite clear. Perhaps the most familiar examples of a vector space are when we're talking about R2 and R3. So we're talking about points in the plane or points in 3 space, and the vectors are those tuples which consist of, just the points, or you could think of the vectors visually as the arrow that comes out from the origin to the point in the plane or the point in 3 space. So those are the vectors that you're looking at, and those are vector spaces over the real numbers, where the action that we have is you take a real number and it acts on a vector by component-wise multiplication. Now, you could generalize that, and you could move from R2 or R3 up to Rn, but you can generalize a little more fully even then by saying suppose that F is any old field, doesn't have to be the real numbers, and you could look at the vector space F to the n, which is really just the set of n tuples of elements of the field. And this is going to be a vector space over the original field. The action will be multiplication component-wise in each of the components of Fn, and this, in that way, Fn is going to be a vector space over that original field. Now, in the previous two examples, when we're looking at R2, R3, or Fn, you're talking about the vector space V actually being a field itself. This doesn't need to be the case. We only require that the vector space be an abelian group. So here's an example. If we take our field to be F, which we'll just denote by F, and we look at M sub n of F, the set of n by n matrices with entries from the field F, we consider that a vector space. Then M sub n of F is a vector space over the field F. I have it written as field, but I meant vector space. And the action that we have of the field on the set of matrices is just we multiply each entry of the matrix by the scalar from the original field. And now let's take a non-standard example, but an important example to us. I'm going to actually introduce two fields again, so sort of returning to the nature of the first two examples. Let's take E to be the field that's obtained as a factor ring of Z mod 2Z adjoined X, modded out by the ideal generated by x cubed plus x plus 1. We saw earlier in some of these slides, and we also saw in Galilean, that this is in fact a field of order 8, since the polynomial x cubed plus x plus 1 is irreducible over Z mod 2Z. And let's take the field F to be the collection of the additive and multiplicative identity of this factor ring. So the additive identity is just the ideal generated by x cubed plus x plus 1. Multiplicative identity is 1 plus the ideal generated by x cubed plus x plus 1. And this is also a field. So in this business, we want to view what I've identified as F, as our conventional F, and we want to view what I've written as E as the set V from the previous example. And it turns out that E is a vector space over F, and this is an important type of example. What is the action here? The way that F acts on E is just by coset multiplication. So when I take any old element of E and I act on it by an element of F, the thing that I get back is, if I multiplied by the additive identity, then by zero product property I've got 0, and if I multiply by the multiplicative identity, I just get the original coset back. What this is a particular example of is the following, which is something that will be very useful to us when we study field theory. If we have E and F, and both of them happen to be fields, and the field F is a subfield of the field E, then the larger field E happens to be a vector space over the field F, where the multiplication by the scalar is just the multiplication that you have within the field. The next thing that I'd like to cover is the definition of a linearly independent vector. So I'm straying a little bit from the way that Galilean defines this, because I want to define this even for infinite dimensional vector spaces. This we'll cover later on. But let's suppose that V is a vector space over the field F, and let's let S be a subset of V. If there exist vectors, v1 through vn, where n is some natural number, and scalars a1 through an, where not every single one of those a sub i's is 0, and if we happen to have the property that a1 v1 plus a2 v2 and so on and so forth plus a sub n v sub n is equal to 0, then what we're going to say is that the set S is a linearly dependent set. Now the way that I'm going to define linearly independent is to just say not that. So if no such collection of vectors and scalars exists, we say that the set S is linearly independent. Now I'm going to make a couple more definitions. I'm going to do the definition of a subspace and the span of a set of vectors. So in all of the following definitions, I'm going to use the standard notation. V is going to denote a vector space over the field F. Now let's suppose that U is a subset of the vector space V, and it happens to be a subgroup. Then we say that U is a subspace of V if U happens to be a vector space over the field F with the same scalar multiplication. So you have to just be slightly cautious about this. You need that little clause on the end. We've seen this a couple times throughout the semester, as with subgroup and subring and so on and so forth. We always have this clause under the same operation. That means, for instance, that you can't change from standard multiplication to multiplication modulo something. That would be changing the operation of the vector space, and so that would kill this property. So it needs to be the exact same operation. And now let's suppose that S is a subset of V. Then we're going to define the subspace spanned by S, which we're going to denote with those angled brackets as we have done so far. The subspace spanned by S, denoted angled bracket S, angled bracket, is the intersection of all subspaces of V containing S. Again, this is a little different from the definition provided by Galilean, because this is the definition that works no matter what is true about S and V. I haven't made any kind of assumptions about anything being finite, as your book does. However, most of the vector spaces we're going to be interested in when we jump into field 3 are finite vector spaces and finite dimensional subspaces. So let's just take a look at what happens if the subset S that I take of V is finite. And let's say the size of that set S is n. So there's n vectors sitting inside of S. Then, It's equivalent and perhaps more useful to think about the subspace spanned by S as the set of possible linear combinations of the members of S. So that's all things of the form A1v2 plus A2v2 plus and so on and so forth plus A sub n v sub n, where all we require is that the A sub i's belong to the field F. So all possible linear combinations of scalars from the field and the elements of the set S. So this is the most useful one when you're dealing with a finite set. However, I wanted to include the previous definition just in case we're talking about something that is not finite. Last but not least, in terms of definitions, I'd like to introduce the definition of a basis and a definition of the dimension of a vector space. So again, in all that follows, we're going to write V for the vector space and F for the field. And let's suppose that S is a subset of V. We require two things. If it happens to be the case that every element of the vector space belongs to the subspace spanned by S, and if the members of S are linearly independent, then we are going to say that S is a basis for the vector space V. So it's some hopefully smaller collection of elements, so we don't have to include every single vector, we have just a subspace of vectors, but really we can build everything in V in a unique way out of the members of S. So S is sort of the minimal amount of information that we need in order to reconstruct the set V. That's what we think of as a basis. Last but not least, let's suppose that S is a subset of V. Let's suppose that S is finite and that S happens to form a basis for V. This is the case we're really going to be using quite often when we work into field theory. Then we say that V is a vector space of finite dimension, and what that finite dimension is the cardinality of the set S. If V is not spanned by any finite subset, then we will say that V is an infinite dimensional vector space over the field F. So we use the words finite dimensional vector space and infinite dimensional vector space over the field. Now, just to make this a slightly less boring presentation, hopefully, let's do some examples just using the previous terms. So let's consider two different vector spaces over two different fields. Let's introduce the vector space V, which is the rational numbers adjoined X, so polynomials with rational coefficients, and let's let V primed be a similar vector space. Let's have it be a polynomial ring, but a factor group of a polynomial ring. So we'll take the polynomial ring, which is coefficients in Z mod 3Z, and let's just mod out by the ideal generated by X to the fifth to get V prime. So we're really looking at just polynomials whose coefficients are in Z mod 3Z and whose maximum power is in X to the fourth power. Let's let F be the rational numbers and let's let F primed be Z mod 3Z. So in this way, the vector space we've identified as V is a vector space over F, and the vector space we've identified as V primed is a vector space over F primed. Dealing with this first example, V, here's a nice example of an infinite dimensional vector space over F. This is a good example because sometimes people think that the vector space V is finite dimensional of order 2. They somehow think that 1 and X generate the whole polynomial ring. It's true if you allow yourself to multiply the x's together, but remember that this is a vector space, so we're really only allowed to deal with addition. We haven't required there even be a multiplication inside the vector space. So what we really need is we need an element 1 in order to generate all the members of Q, and then we need x, x squared, x cubed, x fourth, and we actually need every single power of x in order to build every single polynomial we could imagine. And so that set, 1, x, x squared, x cubed, and so on and so forth, is an example of a basis for V. I should say, and I didn't say it when I defined basis, but it's kind of important to note here, is that a basis is not a unique thing. There are many, many, many different bases for given vector spaces. And so you've just got to, there's nothing unique about it, although a lot of times, depending on your context, there's a, quote, most natural, quote unquote, selection of a basis. And here I think this set S is a pretty natural one. Now let's look at the set T, which would just be 1x and x squared, and let's look at an example of what's the subspace spanned by T. So T is a nice finite set. The members of T happen to be linearly independent, means I can't take any combination of rational numbers and add a rational number times x squared plus a rational number times x plus a rational number times 1, and I can't get 0 unless every single one of those rational numbers is 0. So that's what I mean by these things are linearly independent. And the subspace spanned by T would be the set of all polynomials with rational coefficients of degree at most 2. Switching to the other example, here's an example of a finite dimensional vector space. So V primed is a vector space over F primed. It has finite dimension, and that dimension is 5. A very similar set, S primed, which is 1x, x squared, x cubed, and x to the 4th, forms the basis for V primed. So here I'm not going to prove that, and I'll leave that to you. I think it's pretty easy to show that S prime spans, and it's equally easy to show that if you take any combination of those elements and add them together and happen to get the 0 polynomial, that the things you were multiplying by had to all be 0. That's pretty easy. But just for a little bit of a change of pace, let's take a look at the set T primed, which would be x plus 1, x, and the element 2. So 3 different members of V primed, and this happens to be a linearly dependent set. And to show that it's linearly dependent, what I need to do is take these elements, find scalars inside my field, F primed, to multiply them by, so that when I add them together I get 0, and I want at least one of those scalars to not be 0 itself. So here my scalars are 1, 2, and 1. And I take 1 times x plus 1, I add it to 2 times x, and I add it to 2. What I end up with is 3x plus 3, and inside my V primed that happens to be 0. Last but not least, I just want to give a final example dealing with how do I find out the dimension of a vector space if it's finite dimensional, and typically the easiest way to show what the dimension of a particular vector space is to just exhibit a basis and look at the size of that. Prove that you have a basis and then just count the number of elements you have in your basis. So here, let's let V be the set of matrices with rational entries that have this particular form, A, B, B, C. So we have this matching diagonal, not the main diagonal, but the opposite diagonal. And all we require is that A, B, and C are rational, and let's let F be the rational numbers. So here's matrices over the rational numbers, 2 by 2 matrices. Let's find the dimension of this vector space V as a vector space over F. So like I said, what I'm going to do to find the dimension is I'm going to give a basis. So I'm going to find a set. The set I'm going to choose is the set of 3 matrices, the matrix 1, 0, 0, 0, the matrix 0, 1, 1, 0, and the matrix 0, 0, 0, 1. And I'm going to claim that this set happens to form a basis. So what I need to do in order to show that this set is a basis is I need to show the 2 things required by the definition. So first of all, I need to show that this set spans the space, and then the next thing I need to show is that if I take any linear combination of these things and end up with the 0 matrix, that the scalars that I multiplied by had to in fact be 0 themselves. So this all basically comes about from this one equation that we have written on the page. If I take a matrix A, B, B, C, then this is equal to A times this first matrix plus B times my second matrix plus C times my third matrix. And this is pretty easy to figure out just knowing what the action of the field is on the vector space and knowing how to add matrices together. You can pretty easily see that that equation holds. And that, first of all, just that equation is enough to show that the elements of S span the space. Because I took any old arbitrary element of V, A, B, B, C, and I wrote it as a linear combination of the members of S. So that shows that these vectors span the space. In order to show that these vectors are linearly independent, assume that I have A, B, B, C as I have on the left of this equation here, and suppose that's the 0 matrix. Well, then that would have to be equal to A times 1, 0, 0, 0 plus B times 0, 1, 1, 0 plus C times 0, 0, 0, 1. Each of A, B, and C is 0, and that's the only way to do that, because this is an equality. Left and right is the same here. So it's pretty easy just from this simple equation to show that this set S is the basis for this vector space. And since there are 3 elements in S, it's a vector space of dimension 3. In summary, after studying these slides and the chapter on vector spaces in your textbook, and from your previous knowledge of linear algebra, you should both know and fully understand the definitions of a vector space, the linearly independent vectors. You should understand the span of a subset, the basis of a vector space, and the dimension of a vector space. And you should really understand these things both for the finite and infinite dimensional cases. So that takes into account the slightly different wording that I've used in this set of slides than what is used in your book. The second thing is I would hope that you feel comfortable working in non-standard examples, so maybe try to get your feet wet using examples like factor rings to form your fields. And maybe work with an infinite dimensional vector space or two, since I think this tends to be a little bit less touched in a standard linear algebra class. And last but not least, perhaps it's a big jump, but I'd really like you to be able to open up to chapter 19 of Galleon and virtually solve any problem that's there. I think when I look over chapter 19 and look at the exercises, almost everything there is pretty standard, or seems like it should be easy enough if you understand what you're doing with vector spaces. In particular, if you're looking for things to focus on, I'd say look at problems 9 and 10, 14 and 15, and 27 and 29. I think those are pretty decent places to start to just make sure you really understand the heart of vector spaces so you're ready to move on to field theory and module theory.